Let's now continue with electrodynamics. And after having introduced the theory, derived the equation of motions of charged particles in electromagnetic field, before arriving at the derivation of the equation of motion for the field itself, I would like first to discuss the scenario in which we have more than one particle, and therefore I'm going to define the four density current, so whenever we have a density of particles, and what is the connection between the continuity equation and the gauge invariance. So let's get started. And what we have, again, are many particles. I'm going to introduce the four current density, and in doing that I'm starting with the action whenever you have more than one particle. Okay, I just recall that the action for SPF, so particle field, is Q over C integral between A and B of A mu dx mu, and we've also seen that this is also equal to QC integral between A and B of A mu J mu, where it is the current density for one particle, and integrated over the T. Well, I remind you again that J mu in this case is equal to CQ and the standard three-dimensional velocity current, which is J equal to QV. This is for one particle. Okay, good. Then let's start to introduce more particles. And what you have are more particles that now I'm going to draw. And what we do is to define infinitesimal volumes in which there is a certain number of particles according to their number density. Okay, therefore, from number density of particles, whenever we multiply the contribution of the charge for each particle, we get the density charge, the charge density. For what we have is that for each volume there is an infinitesimal amount of charge which we can associate to a density times a volume. So you see rho is a density over volume, is a charge density. Charge density. And whenever we want to have the finite amount of charge that we have in a certain volume at a certain position in space, this is three-dimensional space, that's equal to what? Is the sum of the charges that we have. Now I'm expressing this function as a continuous function for all positions in a three-dimensional space, and I can simply introduce a delta function such that I have that this function here is equal to 0 everywhere except where there is a charge. In fact, the delta function is equal to 1 when r is equal to minus rj. Okay? You still see there is the sun now. Move a bit. Okay, good. Okay, and now when we go to the continuous limit, we can represent the finitesimal, the finite density as the integral over the volume R of rho dV. Okay, so we are going from the discrete situation to the continuous case. Continuous limit. Okay. Now I would like to stress something, because when we introduced the action for the particle field interaction, we defined that Q was an invariant, is invariant because it is a constant and do not transform under Lorentz transformations. Whereas rho is not an invariant. That's because rho is defined, as it's written here, as a charge, which is an infinitesimal charge, is invariant, but such a like the Q, because it is a charge do not transform, but it's divided by the infinitesimal volumes. And volumes is a length times a length times a length, and as we know, length transform under Lorentz transformations. Therefore, this guy is not invariant. But all the time that we are dealing with this sort of collection of particles, we are always going to the Q, which is an invariant because the volume, the V, vanish. Just do it. Want to be tedious on that. So we are the charge, the V. This is by definition the Q, the V, and the length disappears. Okay, just to be super sure. But you got the idea. Okay, let's now introduce let's start to move toward the situation in which we are considering more particles. And first, let's give a look at the action for an infinitesimal amount of charges. Therefore, we have the SPF, which is equal to dq over C integral A mu dx mu between A and B. Okay, it's exactly like this one, but it's just an infinitesimal amount of charge related to an infinitesimal volume. Okay, let's now express this dq with respect to the charge density. Therefore, we have rho dV C A B E mu dx mu. Fantastic. Now, I don't know if you can still see, I don't see anything. Okay, I hope you can see, otherwise I have to show the video again. Now let's start to get the action whenever we have the infinitesimal action associated to this infinitesimal portion of volume. If we want to have the total, what we do is to integrate over the volumes. Therefore, the action SPF. Now I'm not going to relabel this one for the continuous situation, so from now on, whenever you see SPF is not of an individual particle, but it is of a collection of particles. Okay. Good. So what we do, we just integrate this function here. Therefore, we have 1 over C. Then we have the integral between A and B. We have rho A mu dx mu the volume. So this is a double integral, also over volumes, of where the density again is a function of space. Okay, because the density can change as a function of space. So rho is like that. Okay, good. Now what we do, I want to go in the direction of defining again the Fourier current. For what I do, divided by dt multiply by dt. And now you see that now I have a rho dx mu over dt, 1 over c, then I have my integral a mu, and I define it as my new j mu that has a new meaning now, so I still have the volume dt, and j mu is equal to rho C rho V, where I define now the density current as J rho V. So you see it's very similar to what we had before, but instead of having a charge, we have a charge density and charge density. This is the Fourier current density. Okay, and you can distinguish that this SPF is not like the one before, because before was integrated over the t, now we have a dV over the t. And for convenience, I can define this dV the V dt, which is what? The x1, the x2, the x3, and then we have the t that I can divide by c and multiply by c. What is this guy here? That's the x0. Oh, sorry. It's this one is the x0. Okay, therefore I have the x1, the x2, the x3, the x0, and I define it as the omega. So the omega is the product of all the x1, 2, 3, and 0, or of all the 4 dimensions, and I have this c here. Therefore, once I can define this 4-dimensional, so is in the infinitesimal volume in the Minkowski space divided by c, which is 1 over c squared. So the c squared is coming from here. And then you have the integral over a and b, now let's be explicit, and over the volume that we are considering, where there are the charges, of a mu j mu the omega. Okay? Now, last consideration about the 4 current, J mu. What is it? Just to look at the unit of measure. So J mu, the units, are what? A density current. Sorry, is a charge density. Therefore, are Coulomb over meters cubed times a velocity, which is meters per second, and this thing is equal to Coulomb, meters cubed, so meters squared over s. These are the units of a flux. Oh god, you couldn't see it. So just repeat, units of J. Then we have, so J is a density charge, therefore c over meter cubed, times a velocity, meter per second, which give us Coulomb meter area per seconds, and this is the flux. Okay, so it's the amount of charges that are flowing in an infinitesimal amount of time across a certain area. Okay, this is a flux. Now that we have the 4 density current, we can derive the continuity equation. Which is basically expressing what is the time variation of the charge for these individual volumes. Time variation of charge for the volumes, which is what? Is simply the derivative with respect to time of the charge of those volumes. Therefore, rho dV. So this is the charge, and how is it changing as a function of time. Then how is it, why is the charge going to change? Well, because the particles are going to flow from one volume to another one. And this is given by what? This is given by the flux. So this is given by the 4 current. Okay, we have seen before the units. This is a flux, which is charge over area per second. Therefore, if you want to know the time variation related to a charge, is going to be to J the S, which is in fact rho V the S. And if I want to write it into Einstein notation, Vi the Si, where these are only the space components. Okay, let's give a look at the units. So as we said, this J mu is the flux, therefore is the charge meter squared per second. That's what we wrote before. times an area which are meter squared. This goes away. You see, this is a charge over second which has the same unit of t. So this is how the charge is changing as a function of time can be related to the flux, so how particles are moving around. Good. Now, how do we measure, how do we quantify this area? Because it might be weird that an area is actually expressed as a vector. Well, that's easy to say because areas, surfaces, if we take, now imagine a volume, okay, whatever its shape, we can define this small surface that stands over the area, and we can define it as the vector pointing inward. So this is the area, and the vector, this is the volume, this is the surface around defining this volume. The area is defined as a vector orthogonal to the surface of this volume, pointing inward, so pointing inside the volume. And now you will understand why, okay? And the length of the vector, so the modulus of the vector, represents the surface of this area, okay? And here you have a scalar product because you have the flux, which maybe is not pointing orthogonal to the area. Why? You define a volume, the flux could be pointing in this direction, right? Therefore, can also be not orthogonal to the surface that we are considering. So this is J, and this is the S vector. And in fact, if I have a flux like this is the area, and I get a surface which is like that, so the scalar product, so the vector of this, so I don't know, like this. So if this is the flux and this is our surface, like this I have the maximum, like this I have 0. You see the two vectors of the area and of the flux are equal to 0, and I don't have an outgoing flux of particles. They are always staying inside the volume. Okay, so now you understand why the area is defined through a vector of this sort. And this is inside, and this is outside the volume. And it's pointing inward because you want that the numbers of particles within the volume is going to decrease if the flux is pointing outside. Okay, therefore that's why you define the area pointing inward, such that if the V, the S is smaller than 0 for an outgoing flow. That's not an if, for an outgoing flow of particles. Okay? Good. Now we have these two bits of information, so we know this is the time variation of the charge, this is the time variation of the charge, the two must be equal and opposite, and therefore we have that d over dt integral of rho dv must be equal to minus the integral of j ds over of the integral of j ds, and this is done over the entire surface defining this volume. Now we can apply the Gauss theorem. Three-dimensional, because we are always acting on space components. So that's equal to the integral of the gradient of j with respect to the volume. Now we can put these two, you see I have integral of volume, I can put these two things together. So I'm going to have the integral of, now this is delta, so that's derivative, that's the integral, two linear operators, I can invert them, so I bring the derivative inside. We have d rho over dt, oh, there is the minus that I forgot the minus here, which is this guy here. I bring it on the other side, therefore I have a plus gradient of j integrated of the volume equal to 0. But this equation must be true for every volume, because I can define the volumes as I want, but this equation still have to be true, which means that the actual final equations is the rho over the t plus gradient of j equal to 0. This is the continuity equation. For the charge. Okay, and this equation expresses charge conservation. And in fact, it's going to tell you that the charge is going to change, not because it is destroyed, but because it moved around. Okay, so it expresses charge conservation. And as I said, we are going to see this equation again, because now we used a charge density, but we could define a matter density. And therefore, whenever we have rho, which is expressed as a matter of density, kilogram per unit of volumes, then it's going to express matter conservation. Okay, so that's why we are going to see again this equation when we are going to discuss hydrodynamics. Now that we learn how to deal with a collection of charged particles by introducing the charge density and the 4 density current, and after having learned how to compute, how to relate the time variation of the density of a certain volume with respect to the flux of the particles through the continuity equation, which is expressing charge conservation, that's because it's going to tell us the time variation of the charge within a certain volume is related to the fact that particles are moving from one location to another. They're moving from one volume to another, one direction or the other. Okay, you can have an outgoing flow or an ingoing flow, and this creates the change of the charges of the charge within that volume. It is expressed charge conservation because it's going to tell you, look, charges are not going to be created or destroyed, but they're just moving from one location to another. Okay, now let's give a look at how the continuity equation, therefore charge conservation, is related to the gauge invariance. And we do that by looking at the action as Pf of our collection of particles, which is related to the density rho, and gauge invariance, so this one we have seen it already, is basically like that. So we have our 4 potential, we want to gauge it, therefore we have a new one, a new potential, which is equal to the original one plus the gradient of an arbitrary function. Okay, so we know when we make this sort of transformation of our 4 potential, the equation of motion is not going to be affected. We are going to find the same result. The relevance of this transformation, of this gauge invariance, is that I am free to add this gradient to my 4 potential, and all equations are not going to be affected, and I can therefore introduce this gradient to simplify my life. Okay, I can just simplify the mathematics, because, for example, I could define this function here such that my transformed 4 potential is equal to 0 t, at. Okay, so therefore I can make a transformation such that the scalar potential vanishes, and then this simplifies my life in the derivation of all the equation of motions and so forth. Okay, so that's why this is relevant. And this is also going to tell you, this is also telling you that the 4 potential is not uniquely defined. Okay, because you are always free to change it by adding such a gradient. Okay, so this guy is not unique. If you change a mu in this way, you are going to find an electric and a magnetic field, and therefore an electromagnetic field, which is always the same. You are not going to be touched. Okay, Very good. Let's now to transform the action by using this new a mu tilde. So our SPF, so the action for the interaction between the particles, plural, and the field transformed, is equal to 1 over c squared, the integral of this action a mu, a tilde mu, j mu, the omega, which is equal of 1 over c squared integral, and we have these two components, therefore we have a mu plus the f over the x mu multiplied by j mu in the omega, which is equal to the original action, because we have this a mu j mu in the omega, which is exactly that, plus 1 over c squared, and now we have the integral of our beloved gradient, the x mu times j mu in the omega. And now what we do, we play a little bit with this quantity, because this is the gradient of a function times our 4 current density j. But I can play a little bit and look how this is related to the gradient of f times j mu. Okay, so it's the gradient of the product of the two. So I'm basically multiplying, I'm looking what is the gradient of j multiplied by a scalar function, which is equal to, let's apply now the chain rule to the derivative. So I have the derivative of the first equation, the f over the x mu, times the second equation, plus f times the derivative of j mu over the x mu. Okay, and you see that I did that because I extracted this term, which is equal to this guy here. Okay, and on top of that I have this term, but look at this guy here. This is the mu j mu, which is equal to 0, and it is equal to 0 because this is the continuity equation written in Einstein notation. Okay, so you see you have the derivative with respect to the time plus the gradient. This is a 4 gradient that you can write it like that. Okay, that's equal to 0, that's equal to 0, so this is the condition that expresses charge conservation. Therefore, because of charge conservation, this guy is equal to 0. And therefore I can substitute this quantity with this one, and then use the Gauss theorem. That's why I looked at this trick. Okay, because I wanted to go in the direction of the Gauss theorem, to apply then the Gauss theorem. So let's do that. Now I can substitute this guy here with this object, because they are equal. This is equal to 0. Therefore I have the SPF plus 1 over c squared. Then I have the integral of this guy, so the gradient with respect to the x mu of fj mu, yes, the omega. Okay, and now I can apply you see that I have the integral over a volume of the gradient of a function. Therefore I can express it, I can use the Gauss theorem to express it as the integral of the surface enclosing this volume of the function, and this is over the area, so the S mu. Okay, good. And look, this guy here is constant. Fantastic. And now you see why I said that with this Gauss invariance, by doing that, I am not going to affect the equation of motions, because the equation of motions are obtained by using the least action principle, the S, in this case tilde, which is equal to the SPF, because when we apply the variation of this object, we have the variation of SPF, then we have the variation of a constant which is equal to 0. Therefore, we obtain the very same equation of motion. Same equation of motion. So basically, you see by that continuity, the gauge invariance is there, and the physical reason for it to be there is because the charge conservation, which is expressed by the continuity equation, holds.